Really nice introduction. And thank you very much for having me. I'm really honored to be here. Um, like introduced, my name is Shuangning. I'm currently an assistant professor of econometrics and statistics at Chicago Booth. And the topic of my talk today is this covariate adjustment and balancing under interference. So this will actually be a combination of two works. And this is, sorry. This is a joint work with three amazing collaborators, Xinyi, Zhang, and Xinran. So, like I said, this talk will have two parts, and the first part will talk about how do we do covariate adjustment under interference, and the second part will be focusing on how do we do a covariate balancing with re-randomization. And then, so the first part is a joint work with Xinyi. Xinyi was a master's student at the stats department at U Chicago. She went to Berkeley for her PhD. And then the second part of this talk is still an ongoing work. So any comments or questions are super welcome. And this is a joint work with Zhang and Xinran. Zhang is currently a master's student at the stats department at U Chicago, and Xinran is my colleague at the stats department at U Chicago. Okay, great. So let's actually get started with the topic today. So if we look at the title here, you'll notice that the title of my talk is Covariate Adjustment and Balancing Under Interference. And you might wonder what I mean by interference here. So I'm going to start with telling you a motivating example. And here I give a slight hint of what this motivating example is going to be about. It's going to be about weather insurance. So hopefully through this motivating example, it will become a bit more clear what I mean by interference, and specifically how interference would complicate causal inference. And then in this same example, we will also see that fortunately, we also have some covariance information that we want to utilize to improve our causal inference. And the key question that we want to address is how should we utilize those covariance information to improve causal inference. So with that, let's go into our motivating example. So this is an example that's taken from this amazing paper by Cai et al. 2015. I do want to say that the current version that I'm presenting of this example is a simplified version of what they actually did, but hopefully this serves well as a motivating example. So in this paper, we have a bunch of researchers. They go to this rural village in China. They get a bunch of farmers. Okay, they decide to run some randomized experiment. So how do they do that? They just toss coin to randomly separate our farmers into treatment group and control group. So all the red people get into a treatment group, all the blue people get into control group. Okay, and then all the treatment farmers are asked to go to this information session where they're going to learn about the benefit of a weather insurance. So during this information session, they're going to hear things like, hey, if you get this weather insurance, even if the weather turns out to be bad, you can still get your money back. And if you don't get this insurance, your financial situation would be much more risky. And in the control group, you don't go to this information session. Okay? And the researchers are interested in this question of what is the effect of this information session on farmers' financial decision to purchase the weather insurance. We would usually imagine that maybe the farmers don't know much about weather insurance, and after they learn about this in the information session, there is a higher chance of them purchasing the weather insurance. Okay? And you might think this seems to be a very simple question and almost the most standard causal inference question because we get data from the treatment group, we get data from the control group. We can just look at what's the percentage of people getting this weather insurance in the treatment group, what's the percentage of people getting this insurance in the control group, and then take the difference of that. And that hopefully already gives you some information of the causal effect of this information session. So we'll see in a second that this is not entirely right. Something more complicated is going on in this case. In particular, what's going on is the following. Our farmers are human beings, and human beings can gossip with each other. So let's say that I'm this control person, this blue person in the control group. Let's say Jing is this red person in the treatment group. I didn't know anything about weather insurance. I didn't go to the information session, but my friend Jing went to the information session and learned about the weather insurance. And she could be calling me and telling me that, hey, Shuangning, I went to this very interesting information session and learned that weather insurance seems to be a interesting thing. You should probably also look it up to see whether you want to get it. So what we see here is this information of the information session gets spread from the treatment group to the control group. So then this control group in a way is not like a pure control group because people get information from the treatment group. So it's not clear anymore if we still do the standard causal inference method, this is still actually going to give us the thing that we want. So I'll make this slide a bit more precise on the next slide. But formally, we call this phenomenon interference. And interference is defined as this phenomenon of the treatment assigned to one unit may affect outcomes of other units. In this particular case, the treatment is whether someone go to the information session or not, and the outcome is their financial decision of whether they purchase the weather insurance or not. And in this case, we see that Jing's treatment, because Jing went to this information session, she know about this weather insurance, have an impact not only on their own treatment, on their own outcome, but also have an outcome, have an impact on my outcome. So that's what we call interference, or sometimes we also call this cross-unit interference. Okay. And then, so as we've seen before, I've talked really very briefly that interference can actually makes causal inference more complicated. And let me actually be slightly more precise what I mean by that. So let's consider this case where we are interested in estimating something called the global average treatment effect, which is what happens when we treat everyone versus what happens when we put everyone in the control group. So this is the difference of the average outcome in those two worlds. So why do we care about that? If this ends up to be something that's really large and is larger than the cost of launching an information session, and if we think that this phenomenon would generalize to other villages, then if we want to sort of help the farmers stay away from risk, we would want to launch this thing to other villages in the future. So this is a pretty policy relevant estimate. Okay, so let's say we are interested in estimating that. But we don't see this, right? Those are two counterfactual worlds. The only thing that we can see is this data that we get out of the experiment where we put 50% of people into the treatment group and 50% of people into the control group. In the classical causal inference world, we would think that those red people is representative of those red people in a 100% treated world, and those blue people are representative of the blue people here in this 100% control world. The problem here is that with interference, this does not hold anymore. And let's actually just look at the control to illustrate this. Like I said before, in this world, 100% of the farmers are in a control group. Probably very few of them know about the weather insurance. Now, those 50% of, if we have 50% of people in the treatment group and 50% of people in the control group, even though the control people, the blue people here, didn't go to the information session, they probably have heard a little bit about the information session about the weather insurance from their treated friends, from like some of the red people here. So there are conversations going on between the red and the blue. So we would imagine that in this world, when there are 50% of people treated, those control people knows more about the information session, about the weather insurance, than those people where when we put 100% of people into the control group. So formally, what we say is that if we consider this difference in means estimator, which is defined as the average outcome of the treated units inside the experiment minus the average outcome of the control unit inside the experiment, this is an estimator called the difference in means estimator. This estimator is going to be biased for the causal estimate that we care about, which is the global average treatment effect here. Okay. So this example is basically telling us that interference brings some challenges into causal inference. And specifically, we've seen that some standard estimators, the simplest ever estimators in causal inference, may fail under interference. And thus, we need some new estimators to adjust for interference. And one thing that we didn't really talk about, but from the literature, that sometimes even when the point estimators remain valid, you also need to develop new tools to handle the inflation in variance estimation. In your variance estimation, you also need to account for interference. Okay, great. So that's the first thing that we learned from this motivating example. Now let's consider, let's like continue looking into this example. In this example, um, the researchers not only collect information about whether farmers go to the information session or not and their financial decision, they also collect a bunch of other covariates information. They actually did the survey with all the farmers and asked things about them. For example, they asked about the gender of their household head, they asked about the age, the education of the household head, they asked about the rice production area, they asked a lot about other things. Okay. So when we have those information in our hand, we don't just want to throw those information away. We want to ask ourselves the question of how do we make use of those information to hopefully improve the precision of our estimators. Okay. So, and this is not specific to this interference problem. In causal inference, there is a long history and a lot of literature working on thinking about how do you utilize information of covariates. And sort of the key insight here is that yes, we are in this experimental setup, so randomization on average would ensure that treatment assignment is independent of both observed and unobserved confounders. But in finite samples, there are still chance imbalances in covariates that can affect the outcome. So really what that means is that randomization ensures, even without interference, randomization ensures things are unbiased, but there could still be variance there, and your covariates can be useful in reducing the variance. And then when there's no interference, sometimes we also call the Shuangning setting. Shuangning is a setting that means there's no interference. There are papers that show that adjusting for those covariates can mitigate such imbalances and reduce the variance of the estimated treatment effect without introducing bias, mostly asymptotically. However, the story becomes much more challenging in the presence of interference because if you just take the method out of those suitable world and directly use them in this interference world, you'll find that some of the method can actually inflate variance when interference exists. And one of the methods is this direct regression adjustment. This can actually inflate variance. And we'll go into that. We'll make all of this slightly more precisely later. So the take-home message here is that achieving variance improvement uniformly over all cases using covariance information becomes non-trivial. So really, we've talked about two things, two challenges in this interference world. The first is standard estimators can fail under interference, and even if you adjust for that, after you adjust for that, the role of covariates is still unclear. It's not clear that you want to directly do your regression adjustment to make use of the information of the covariates. Okay. So the goal of this talk is to address those challenges. And in particular, we would be focusing mainly on the second challenge. So the first challenge is not like we'll just leave them there. We will actually take methods from the existing literature that sort of already handles that sort of have new estimators or handles the variance estimation problem under interference. So we will be built off on some existing estimators from the literature, and this talk will be focusing on the second point, where we will be developing methods that incorporate covariance information. And the key goal here is to guarantee improvement over no adjustment. Okay. And specifically, we will have two separate parts of the talk. The first part talks about post-experiment adjustment. So what that means is we do our randomized experiment, and after that we collect data. We collect data not only of treatment outcome, we also collect data of covariates. And then we think about in the analysis stage, how do we make use of the covariates information? The second part, we actually do things slightly differently. We utilize the covariates information in the design stage. When we design the experiment, we use the covariates. In particular, in this case, we are trying to enforce balancing of some covariates information in the treatment and the control group. So we'll make all of that more precise later. And then the two paper also make slightly different assumptions and they have different targets. The first paper targets more of a global effect, but the result would rely on something called a low order interaction outcome model. The second one, we target something that's slightly easier called a direct effect, but we can actually, this is a pretty model agnostic method that we don't actually have in order for the variance, so for the covariate adjustment method to be guaranteed to be better than the no adjustment method, we don't actually need any structural assumptions like the low order interaction model in the first part of the talk. And then the first part of the talk, we have a draft of this on archive with this title, Covariate Adjustment Cannot Hurt, Treatment Effect Estimation Under Interference with Low Order Outcome Interactions. And we haven't submitted this yet, so any comments or questions are super welcome. The second part is actually still an ongoing work. I think hopefully we'll have a draft, I don't know, sometime in March or April. And I'm actually just making up the title. I don't even know whether this will be the title of the paper. And so because this is ongoing, so we would welcome comments or questions even more. So with that, I'm gonna pause here to see whether we have any questions, and if not, I'm going into the first part of the talk.
Maybe I'll ask, so I think your example give a very clear idea about what the interference are.
Mhm.
But in general, do people know um, when I'm running this type of experiments, would I in
Right.
general know what type of interference would be there? And does this method requiring knowing the mechanism in terms of how this gonna happen?
That's an awesome question. So in this particular farmer example, the interesting thing being, they actually have this in this survey. They not only actually ask about the covariates information, they actually also ask the farmers who their friends are. They ask the farmers to list the five uh, closest friend that they talk to. So this actually helps us gather information of, we'll talk about this later, of a social network that they think is gonna mediate how interference happens. And so going back to your question of whether the results here would depend on the interference structure, yes, for the first part, no for the second part. For the second part, the result is pretty model agnostic. We don't actually have to know the interference structure. This doesn't have to be like, well, I in the title I say network interference. This doesn't actually have to be network interference. It can be like any type of interference, as long as we have some sparse dependency structure. But the first part, we this sort of heavily depend on this assumption of it's a network interference model. I'll talk about what network interference is, and we have to observe this network in order for this to hold. Thanks for the great question.
Thank you.
Great. So with that, let's go into the first part of the talk. I'll spend more time on the first part than the second part. Okay, great. So a bit of notation. Assume that we have subjects index I from 1 to n. Think about this as we have n farmers. And we denote their treatment by Zi. Zi equals 0 means we put people in the control group. Zi equals 1 means we put I's person in the treatment group. And we assume that we toss coin to decide their treatment. So the Zi's are sampled IID from a Bernoulli distribution with probability pi. And we have this potential outcome model that just says that the outcome is a function of, because of interference, a function of this entire treatment vector Z, like Z1, Z2 up to Zn. And the goal is to estimate something called the total treatment effect, which is if we put everyone into the treatment group, what is the average outcome, minus if we put everyone into the control group, what is the average outcome. Okay, great. So if we look at this potential outcome model, you realize that this is way too flexible because we have this entire vector of z, and z is of length n. Each entry of z takes value in 0 and 1, so there are in total 2 to the power n possible potential outcomes for yi. So this is pretty hopeless if we allow for arbitrary interference because we need to model 2 to the power n possible outcomes. So we want to put some structure on interference in order to make the problem tractable. So what do we do? So the first model that we consider is this network interference model. So this model says the following. There is a known graph with edge side EIJ such that the i's outcome will only depend on the j's treatment assignment if there's an edge from I to j. So and we throughout this paper we assume that this graph is known. So this is a very simple example of this graph. Let's say that we have 5 units, and in this case, 4 is friend with 2, 3, and 5. So this network interference model is saying that because of interference, the outcome of 4 depends on their own treatment. It also depends on treatment of 2, 3, 5, but it doesn't depend on treatment of 1 because they're not friends and they don't talk to each other. So and a bit of notation like Ni denote the set of neighbors of unit I in the graph, and we assume that unit I itself is also a neighbor of itself. Okay. Okay. And so under this network interference model, you notice that this Yi is a function of the z's of its neighbors. So for example, if we look at 4, 4 its friend of 2, 3, 5 and themselves, so the outcome of 4 would be a function of the treatment of 2, 3, 4, 5. Okay? And because all the treatments are just binary numbers, so this function can always be expressed as a polynomial of the z of order the size of the neighborhood. So again, if we look at unit 4 is friend with unit 2, 3, 5, so we could always write the outcome of y4 as a function of the z's in the form of like the first order terms, second order terms, third order terms, and the fourth order terms. And this degree of the polynomial is the size of the neighborhood, in this case is 4. Okay. This is actually still a pretty flexible model. So we want to actually further restrict the model to make things a bit more tractable. And there is this really interesting low order interaction model that we consider. This is a model that's proposed by Cortez et al. 2023. This is an amazing paper, and I recommend anyone who's interested to read the paper. So this paper basically says that we want to further restrict the polynomial degree from the size of the neighborhood Ni down to beta. So and the beta is a known number. Throughout the talk, think about beta as 2. So if we assume beta is 1, then this says that y4 is a linear function of the treatment g2, 3, 4, 5. And if beta equals 2, then it says y4 it's like having linear terms and also second order interactions of those c's. Okay? And slightly more formally, this low order interaction model says the following, says that the outcome yi is a beta degree polynomial of neighborhood treatments. In particular, can be written as a weighted sum of a bunch of products of the z's. Okay? And then, so I do want to emphasize that inside this paper, we don't assume that there is any shared parameters across the units. So by that, I mean that 4 has its own set of parameters C, 3 has its own set of parameters, 2 has its own set of parameters. We can allow for full heterogeneity of the parameters. Okay. And then just to make our like example slightly more general, let's consider an individual I that has 3 neighbors, itself I and J and K. And if beta equals 1, we could always write Yi as like Yi empty set plus the first order terms. Beta equals 2, we have Yi empty set plus the first order terms and the second order terms. Okay, so let's think about what is our goal. Recall that our goal is this total treatment effect. The total treatment effect is what happens if we treat everyone versus we treat like no one. When we treat everyone, all the z's are 1. So each one of the outcome is basically the sum of the alphas. When we treat no one, all the z's are 0. So the only thing that's here is alpha I empty set. So the difference of those two is basically the sum of all the alpha except for the empty set one. So really the total treatment effect that we care about is an average over the sum of all the alpha except for this empty set one. Okay, great. Um, so with that, let's move on to think about how we might want to estimate things like that. The first thing that we notice is that this is a complicated aggregation of the alphas. So if we keep things simple and think about how do we estimate each one of the alpha, then we can just aggregate our estimators of the alpha to form this estimator for the total treatment effect. And let's try to do that. This is what I was saying. If we could construct estimator for each one of the alpha, then we could estimate the total treatment effect. So let's actually start with a simple example. Going back to our example where individual I has three neighbors, I, j, k, and let's say beta equals 1. We've talked about how the outcome in this case would take this form. And we are interested, let's say, in estimating alpha ij, so which is this parameter here. So what do? We multiply zj minus pi on both hand side of this equation. Okay? And then if you take an expectation of this, you notice that this would be 0 because like each zj is a Bernoulli random variable with mean pi. This is 0, this is 0, this is 0, and the only thing that's non-zero is this thing here. So really, the right-hand side has mean 0 except for the term this, and this term, the mean, is alpha ij times pi times 1 minus pi. So this tells us that this thing, if we scale the left-hand side, this can become a non-biased estimator for the alpha ij. So we basically come up with this unbiased estimator for alpha ij, even though the variance is still there, but it's unbiased. So we could do similar things to like the other alphas. And let's see how do we generalize this idea to, let's say, beta equals 2. When beta equals 2, we have this expansion of the y. And let's say we're interested in this parameter alpha I, j, k. Then we could do the same trick by multiplying both hand side with zj minus pi times zk minus pi. Then if you look closely, this thing times anything here would actually give you a mean 0 thing. And the only thing that's sort of not mean 0 on the right-hand side would be this times this. So you could do similar tricks and come up with unbiased estimators for your alpha I, j, k. Okay? So a bit more generally, we could use this intuition for like higher values of beta and like more neighbor settings. And so this actually gives us the SNIPE estimator that's proposed again by this paper, Cortez et al. 2023. So this estimator, it's basically an aggregation of individual estimators of the alphas, and the individual estimator of the alphas takes those form, which is basically like some products of the alpha, like of the z minus pi. Okay, and we could reorganize this. I don't actually remember why this estimator is called the SNIPE estimator. I think it's probably something like structured neighborhood interference polynomial estimator. I think that's about right. But I like this name SNIPE. It's actually pretty simple and concise. So this SNIPE estimator, we could also reorganize it, and it becomes this estimator that looks like this. It's basically a weighted average of the outcome, and the weight takes this slightly complicated form that has something to do with the treatment. Okay, great. So in this Cortez et al. 2023 paper, they also show nice properties of the SNIPE estimator. They show that this is an unbiased estimator. It has a nice variance bound that scales polynomially with the network degree, exponentially with the interaction order beta. And there's an n in the denominator, I think I forgot to mention. And but so like under some network sparsity condition, this estimator, it's consistent and it is asymptotically normal under, again, some suitable graph sparsity conditions. Okay, great. So let's go back to our main theme of thinking about covariate adjustment. So like I said before, there's a long literature. This is by no means a comprehensive list. This long literature shows that covariates can reduce variance and improve precision in randomized experiments. And under this super assumption of no interference, regression adjustment can be shown to be guaranteed to not hurt relative to no adjustment. The story becomes much more subtle when there is interference. This paper, very interesting paper by Gao and Ding, they show that direct regression adjustment can inflate variance relative to unadjusted estimators. And under this is a different framework. Under the approximate neighborhood interference framework of Liang, Lu et al. Developed covariate-adjusted estimators with guaranteed variance improvement. And so in this work, we consider this different framework, the low order interaction outcome model, and we want to see how do we incorporate covariates into the SNIPE estimator to obtain this guaranteed improvement over no adjustment. And a bit of notation denote xi, let xi be our baseline covariates. Okay, so what do we do? Recall that we said that the SNIPE estimator takes this form of a weighted average of the outcome yi. I denote this weight by omega I, and omega takes this complicated form. But really the thing that we need to know is that this weight, omega I, has this nice property of its expectation is zero. Okay, so then we could incorporate covariates in this following very simple way. Instead of taking the weighted average of the yi, we take a weighted average of the yi minus zeta transpose xi. The good thing about this form is because expectation of omega I is zero, so for whatever zeta that you pick that's fixed, the whole thing is still going to be unbiased for the total treatment effect that we care about. And in particular, if we take our zeta to be zero, this corresponds to the unadjusted SNIPE estimator. So the real key question here is how do we pick this adjustment coefficient zeta? So we don't actually have a good idea. So the first thing that we thought about is if there's no interference, what would we do to pick the zeta? If there's no interference, then the yi minus zeta transpose xi times omega would be independent across the units. So then one thing we could do is this takes a regression form, so we should just do a regression adjustment. So how do we do that? We just pick a zeta that minimizes this weighted least square. So it minimizes the weighted sum of square. So this gives us the weighted least square coefficient. We really just minimize the sum omega I squared times yi minus zeta transpose xi squared. Okay, so this is really just like running a regression, but just taking into account that omega I might be different across index I. Okay, and then so we can show that this actually has a pretty nice property that this convergence to the same limit as this the classical results, the adjustment coefficient of Lin's estimator when there is no interference. So like everything seems to be pretty nice if we pick the theta when there's no interference, and it's guaranteed to not hurt. The problem here is we are in this interference setting, so we can't actually just make the simple assumption that there is no interference. So why is this problematic? So the reason is the following. So if we look at this is our estimator, and we need to pick the theta. So because of the existence of interference, those terms are actually correlated with each other. So if we look at the variance of this estimator, there are two contributions. One is from the individual variances of each one of the term, and the other is the covariance across I and J. So if we like the method that we just proposed, we actually call it RAG-SNIPE because it's like regression-based covariate adjustment estimator of SNIPE. This is trying to minimize the variance. So this part is guaranteed to be better if we pick the theta from the previous method. But they didn't actually take into account the covariance part. So the take-home message here is that we should really carefully compute the variance, taking into account covariances. And this is just an example, just like a detailed math on like figuring out the variance and the covariance difference. And you see that this variance part, if you do like this regression-based adjustment, this part is always going to be helpful, but those part is hard to say what happens. Okay. So we need to take into account covariance. And so really we need to carefully calculate the variance and carefully estimate the variance And then in order for us to come up with this better adjustment coefficient theta. So our next idea is let's just work on the variance of this estimator and then find an estimator of the variance of this estimator and then find the coefficient theta that minimizes the estimator of the variance of this estimator. And then so if we do the math and we look at the variance of this thing, this can be decomposed into like complicated terms. But we need to come up with an estimator for the variance in order for us to minimize that. But if we look at the variance form, there are terms that are second order in the alphas, and then there are terms that are first order and zeroth order. The problem with the second order terms in alpha is that they're hard to estimate. Even if we can come up with conservative variance estimators, they're only conservative, they're not consistent. So that's challenging because if we can't estimate that in a good way, then we can't really find the coefficient by minimizing the estimator of the variance. But the good part about this is if we look at the second order terms here, yes, they're complicated, but they don't actually depend on the theta. So what we mean here is that because we only care about the theta that minimizes this, it's fine for whatever things are here as long as they don't depend on the theta. So specifically, one thing that we could do is instead of just looking at the variance, we look at the variance difference between the unadjusted one and the adjusted one. And the difference of the two, when we take the difference, this term actually goes away because this term does not depend on theta. So then if we look at the difference of those two variance terms, those are going to give us terms that are only first order in the alphas and zeroth order in the alpha. And recall that we've talked about how we might want to estimate the alpha. We have this estimator of alpha hat snap where we're like taking this like zi minus pi thing, multiplying things on both hand side, and that's where we got the unbiased estimator for the alpha. So in a way, we have good unbiased estimators for the difference of the variance for the first order alphas and thus for the difference of the variance. And so this becomes our proposal of finding the coefficient. We want to find this coefficient that maximizes the variance improvement relative to the unadjusted SNAP estimator. And that's why we call our estimator the SNAP estimator. Sorry, the Wien-based SNAP estimator, the variance improvement maximized estimator. Okay, so now I this is sort of the formal form of this estimator. I wouldn't go into detail, but recall that what is the pipeline? Pipeline is we get estimators for those alphas, we plug them in, and then we find the theta that maximizes this thing, and then we plug that theta into our adjusted form of the SNAP estimator. Great. So now I'll move on to talk a little bit about the theoretical property of this estimator. We make some assumption on the sparsity of the network. We say that max in degree and out degree of the interference network satisfies its D equals big O of 1. And then this is our theorem. We could show that under some regularity conditions and the sparsity condition, the variance of the Wien snap estimator is asymptotically no worse than that of the snap estimator. Specifically, the difference of the variance times n converge to this form. We access some positive definite matrix. So for whatever theta star here, this is going to be a non-negative number. And moreover, the variance of the Wien snap estimator is asymptotically no worse than any theta adjusted snap estimator. So this is saying that this choice of theta asymptotically gives you the optimal choice among this whole class of like linearly adjusted estimators. And in particular, the difference of the two variants after you scale it converges again to something that's non-negative. Okay? Great. So that's pretty much the theoretical results. I'm going to quickly tell you the simulation results. So here we are plotting the purple curve. We are plotting the mean square error of a few different estimators. The purple curve here and the purple curve here is the original SNAP estimator. And then the blue one here is some model-based estimator that they could have low variance, but they're biased. And then there are also our estimator. This is the regression-based adjustment. This is the mean-based adjustment. And then we can basically see that after the covariate adjustment, we are doing much better than if you don't do the adjustment than the SNAP estimator. And then in like most of the condition situations, you also see that our estimators are better than some of the model-based estimators. Okay, great. So one final thing that I want to say before I wrap up this part is that we have a lot of flexibility in constructing our covariates. The covariates does not have to be just the baseline covariates of the things that we read out of the survey. It could be some transformation of those covariates. It could also be network related. You could not only look at your own rice production amount, you could also look at, oh, for this person, what is the neighbors like rice production amount. Like all of those things can be utilized. You could use like graph neural networks to build whatever covariates that you want. You could also make use of some pre-experiment outcome um, to build your covariates. As long as your covariates stay independent of the treatment, we could use them. Okay, so I think that's it for the first part of the talk. I understand it's already like 8:43 now, but the second part is pretty short, so hopefully we get time to cover that. But I think I'm gonna pause here to see whether there are questions for the first part of the talk.
So I have a question about the numerical experiments you just
Yes,
showed. Um,
yes.
so it seems here, even though the green one is better, but the orange one is also not doing bad, right? I guess the orange one, you just did the regression, assuming like without taking the covariance part into
Right.
account. Is that?
Exactly. Exactly. So, that's a really good observation. So we do actually see that in simulations, the difference between those two estimators are fairly small. Theoretically, we come up with this very adversarial example where we can show that in certain cases, this regression adjusted estimator can be worse than like not adjusting. But I do agree that empirically we don't actually see that. This is actually still fairly good.
I see. And apart from like this linear regression based thing, could you do more complicated estimation for the way covariates could affect things? And if you do come up with a lot of covariates, can you do regularization? Would that affect the way things work here?
That's a great question. I felt theoretically in the causal, even if we don't think about interference, in the causal inference literature, if we want to think about covariate adjustment in this nonlinear way, in like non-parametric ways, for example,
Mhm.
it's hard to get no hurt type of guarantee. So by that I mean like you can't really show that by adjusting it's always guaranteed to be better. But there is this very nice paper um, in the literature. This is not the no interference world where they talk about how you could do a non-parametric, non-linear fit and then use that and then to like think about using that as your covariates and then like do a final like linear adjustment of like whatever you learn from the fancy machine learning tools. So I think like that's the way to get around to theoretically show the nice result of no hurt. Um, but I think practically and like the same thing here. Theoretically, here we have to assume that the dimension of the covariates is bounded. We can't allow that to go to infinity. I think if we work hard in the math, it might be possible. But I think the easy way of getting that around is to do like like learn the fancy function first and then treat those as your covariates, and then do another round of the linear adjustment just to make sure that it's not gonna hurt.
Got it. Thank you.
Thank you. Great. So with that, let's quickly go into the second part, and I hope I could wrap up on time. And so the second part, here I say that covariant imbalance, we've seen this throughout this talk, that covariant imbalance can inflate variance and reduce precision of treatment effect estimators. And in the literature, there are two different ways that you could incorporate covariates. It could be incorporated at the analysis stage, where you could do like regression adjustment or post stratification. And we focusing more on regression adjustment in the first part of the talk. You could also incorporate your covariates at the design stage by what we call stratification or re-randomization. Stratification is sort of your randomizing within stratas where people are like similar to each other. And we will be focusing more on re-randomization. Re-randomization, like I write here, is a simple and effective design stage tool. You basically repeatedly draw an assignment until a balance criterion is satisfied. Note that when I say repeatedly draw assignment, we're not like actually running the experiment. We're just repeatedly draw the assignment on our computer and to check whether things are balanced in the hypothetical treated and control group. Okay, so we've talked about how standard covariate adjustment methods typically rely on the no interference assumption. Many settings interference exists. Under interference is not clear whether standard covariate adjustment method remain beneficial, and existing method ask you to have knowledge of the interference structure, and that goes back to Jing's question of whether we need to know the interference structure or not. Here are two examples. One is this Lu et al. 2024 paper. Their paper they guarantee not hurt only under this approximate neighborhood interference framework. First part of the talk guarantees no hurt, but only under this low order interaction outcome model. So the question that we want to answer in the second part of the talk is how can we adjust for covariance under interference in a way that is robust to unknown interference structure. Okay, and again, a bit of notation: subjects index I from 1 to n, treatment 0, 1, potential outcomes defined as yi, Here I introduce this no notation of notation of yi, zi minus I. I'm just putting zi first. This is relevant for the definition a bit later on. We put zero assumption on the functional form of yi. Okay, so here the target of this part of the talk is different from the first part. We're interested in the expected average treatment effect. This is also known as the average direct effect in the literature. So this is basically if I just keep other people's treatment and move myself from the control group to the treatment group, what is the effect of that? And then what is the sorry, I think I should have like I think there's a typo. I should have like a 1 over n of some I here. So really what I thought I changed this, but anyways, so I think like this effect roughly captures the direct effect, which is the effect of my treatment on myself. And we care about this direct effect, an average over the index. Sorry for the typo. Okay, and then this can be shown. So one estimator for this estimate is the Hayek estimator, which is basically the difference in means estimator, which is just the average of the treatment group minus the average of the control group. And this estimator can be shown to be consistent, assuming some sparsity condition on the dependency graph. Okay, so here we focus on this re-randomization as a design stage approach. So what we do is the following. So consider, let xi denote some covariates that we want to balance. And we define this covariant imbalance measure, which is the difference in mean of those covariates. So in a way, this is sort of the difference of those covariates in the treatment and the control group. So the re-randomization procedure just goes the following. You draw Z from IID Bernoulli distribution, And then you compute this covariant imbalance measure. If this covariant imbalancing measure is small enough, then you take it. And if it's not, then you just repeat until this covariant imbalance measure is actually small enough. Okay, so that's why this is called re-randomization because we are re-randomizing quite a few times. And on this plot, I'm just showing that you would ideally want to achieve this world where things are balanced in the way that we always have three circle faces and three red on both sides. Okay, great. Um, so what we show in this work is that assume that Zi is IID Bernoulli pi, then under suitable assumptions on network dependence, after appropriate scaling, you can see that the estimator minus our target and this like covariate imbalance measure, this would converge in distribution to mean zero multivariate normal distribution. So what that means, this means that if we look at what, so okay, so what is the variance if we don't do re-randomization? The variance of the estimator is basically the variance is this asymptotic variance of this thing here. What is the variance after we do the re-randomization? This basically becomes the conditional variance of this term, conditioning on this thing being small, conditioning on this being small. And this can be shown because of this multivariate normal distribution property. This is always going to be smaller than or equal to the variance of this. And to achieve this, we don't have to know anything about the interference structure. You just come up with your covariates and take that into your re-randomization procedure, and you get the asymptotic variance. It's actually smaller than the unadjusted variance. Okay, so this is what we're saying. No knowledge of the true interference graph is required. Re-randomization is guaranteed to not hurt asymptotic efficiency even with misspecified network-based covariates. But of course, the better your covariates, the better the variance improvement. But just to get the no hurt type of property, you don't actually have to know the true interference graph. Great. This another thing that I want to say is we could all, in terms of building the covariates, in this case, we could actually get even more flexibility. We could build the covariates the way that we were talking about in the first part of the talk based on all the network information. And you can also just randomly guess the network. The network doesn't matter for the theoretical property. And you could actually, in this case, also build your covariates depending on the assignment vector Z. For example, going back to our farmers example, if I think my outcome is going to depend on the fraction of my friends going to the information session, then you can take that as your covariance in this case. Now that covariance would be dependent on the treatment because this would be the average of your average of my neighbor's treatment status. But that's fine. We just re-randomize, and then every time you recompute this to make sure whether the covariance is still balanced in the treatment and the control. Okay. And one final thing I want to say is in this theorem, we talked about under suitable assumptions on the network dependence. I didn't really talk about what are the suitable assumptions. So I wouldn't go into detail here, but here are some sufficient conditions. You could assume that this network is like sparse, or you could also assume that my outcome depends on like many other people, but like how the dependency on those other people's treatment is weak when the two units are far from each other. But importantly, the procedure itself does not depend on like any of the things here. Those are really just assumptions sitting in the theorem. Okay, so I'm going to summarize what we talked about today. Today we talked about under interference, standard estimators may fail. And even when we have estimators that work for the estimate that we care about, the role of covariates in improving precision is not clear. And we talked about two ways of incorporating covariates today. One is post-experiment adjustment, one is design stage adjustment. For the post-experiment adjustment, we study covariate adjustment under interference in this low-order interaction outcome model. Within this framework, we propose this Wien-based covariate-adjusted SNAP estimator with a guaranteed variance improvement over no adjustment. Design stage adjustment, we study re-randomization under interference. This is importantly a model-agnostic approach that incorporates covariates at the design stage and targets some form of direct effect. And we have consistency and asymptotic normality under mild network dependence conditions and a variance improvement without requiring knowledge of the true interference structure. So with that, I'm gonna stop here and to see whether people have more questions. And thank you very much, everyone, for listening and Jing for the amazing questions.